The separation of variables with the time-dependent Schrodinger equation in 3 dimensions to remove the time dependence worked exactly the same way in 3-dimensional space as it did in 1-dimensional space. What we got then was a time part that looked exactly the same as it did before, e to the minus I h bar, or I e t over h bar, as before, and a spatial time-independent Schrodinger equation. So let's take a look at the time-independent Schrodinger equation in 3 dimensions. Consideration of this will lead us to the topic of spherical harmonics, which is very important in many different branches of physics. So we'll spend some time visualizing what they look like. First of all, though, the time-independent Schrodinger equation we got looked something like this. The Hamiltonian operator times psi, acting on psi, is, as before, some kinetic energy operator, p squared over 2m, plus a potential energy operator, v times psi, gives us just a constant e, a separation constant from separation of variables, times psi. Back. Now, the really crucial part of this is this Laplacian, del squared. If I'm working in Cartesian coordinates, the Laplacian is relatively simple. Del squared I can write, and let me suppose that it's acting on a function here, to keep the notation simple, is going to be equal to the second derivative of psi with respect to x, plus the second derivative of psi with respect to y, plus the second derivative of psi with respect to z. The sum of the 3 second derivatives of psi with respect to the 3 Cartesian coordinates. This is our typical Cartesian coordinate system, x, y, and z. If we're working in Cartesian coordinates, great. This is potentially something that we can work with straight away. We'll see what that looks like in a moment. For now, though, I also want to give you an expression for the Laplacian in spherical coordinates. If we're working in spherical coordinates, our coordinate system looks something like this. Just to draw a Cartesian coordinate system for reference, we're working with some point that is a distance r from the origin, and in physics we call the polar angle, which goes from the z-axis to the vector that goes from the origin to r, we call that theta. And the azimuth, the angle around the z-axis here, let me draw that down here, we call that angle phi. So r, theta, and phi for distance, polar angle, and azimuthal angle is our coordinate system here. And in that coordinate system, our Laplacian in spherical coordinates is a good deal more complicated than our Laplacian in Cartesian coordinates. Del squared, acting on some function psi, is 1 over r squared times the partial derivative with respect to r of r squared times the partial derivative of psi with respect to r, plus 1 over r squared sine theta, partial derivative with respect to theta, of sine theta, partial derivative of psi with respect to theta, and yet another term, plus 1 over r squared sine squared theta times the second partial derivative of psi with respect to phi. The reason we have such a complicated expression here is that spherical coordinates are not exactly independent. If I move in phi, for instance, the direction of my r unit vector changes. Consequently, derivatives of functions with respect to a coordinate aren't necessarily directly related to geometrical objects like the Laplacian. The Laplacian is something that is really independent of coordinate system, and since the Cartesian x, y, and z coordinates are all really independent of each other, the Laplacian has a simple expression. In spherical coordinates that's not true, so the expression we get is a good deal more complicated. Substituting in either of these expressions for the Laplacian in whatever coordinate system you want to work in will give you a concrete partial differential equation that you can think about solving. So first of all, let's consider what this equation would look like in Cartesian coordinates. Here's what you get when you substitute the Laplacian with neater handwriting into the time-independent Schrodinger equation in Cartesian coordinates. this is your sum of, and these should be second derivatives. This is your sum of second derivatives of your wave function with respect to x, y, and z. Your potential now must be expressed in Cartesian coordinates as well, x, y, and z. And as before, that's the structure of our equation. What we want to do, if we're trying to solve this equation, since partial differential equations are difficult to work with, is to convert it into a system of ordinary differential equations. And we do that by separation of variables, essentially hypothesizing that psi of x, y, and z is going to be some function of x multiplied by some function of y multiplied by some function of z. If I make this substitution here, plug it in for psi, and find out what I get, well, you'll see what happens. We get something that we can actually separate out into three separate but coupled ordinary differential equations. So substituting in psi as a product of x, y, and z in, say, this term. This term is a second partial derivative with respect to x. That second partial derivative is only going to act on the part of psi that depends on x. It will ignore the parts that act on, or the parts that depend on y and z. So I'll end up with, first of all, my constant minus h bar squared over 2m out front. And then I'll end up with y, z, untouched, and then the second partial with respect to x of, sorry, it's not psi anymore, it's x. When I think about the second partial derivative with respect to y, I'll end up with much the same sort of thing, except it will be the x and z components that are untouched, and I'll be left with the second partial with respect to y of the y-dependent part of the wave function. Likewise for z, x and y untouched, second partial derivative with respect to z of the z-dependent part of the wave function. The rest of my expression here is relatively straightforward. V and then x, y, and z untouched equals e, x, y, and z untouched. I can ensure that these are actually separated if I simplify, and the easiest simplification step is to divide through by your wave function, divide through by x, y, and z altogether. That will cancel out the x, y, and z's here, and it will cancel out the y and z parts with the x and z parts with the y, and the x and y parts with the z. What you end up with then is minus h bar squared over 2m, 1 over x, partial derivative with respect to x of the x part, plus 1 over y, partial derivative with respect to y of the y part, plus 1 over z, partial derivative with respect to z of the z part, plus v equals e. Now if, and there has to be some special circumstances here, if I can express this v in some simple way, if this v does not depend too much on x, y, and z, or if it depends on x, y, and z in a way such that I can put the x-dependent parts there and the y-dependent parts there and the z-dependent parts there, I can split this up. Looking at this then, I have something that is a function only of x, something that is a function only of y, and something that is a function only of z, plus potentially some constants coming along for the ride. If I have something that's only a function of x, and something that's only a function of y, and something that's only a function of z, all added up, and I want this equality to hold for all values of x, all values of y, and all values of z, the only way for this to work is if this is a constant, this is a constant, and this is a constant. These functions that I have must be essentially trivial functions in order for this equality to hold regardless of whatever I plug into the function as an argument. So for instance, in the case of this x term, I end up with a partial differential, an ordinary differential equation now that looks something like this, minus h bar squared over 2m times the second derivative with respect to x of the x function divided by the x function is equal to some constant. I don't necessarily know what that constant is, I don't necessarily know what a good form for this constant would be, but I have a function only of x, and it's a differential equation involving that function. And the differentials are only with respect to x. So this is an ordinary differential equation. X is the only variable in this equation. It's the sort of thing that you could think about solving for x. You'll end up then with relationships involving these constants, And if you flip back in your notes, back to when we talked about how separation of variables worked in one dimension, you get a feel for what this sort of thing looks like. You can solve this equation, you find the x portion of the wave function, you can then go back and combine the different variables together in the same sort of way as we combined adding a time part back to our spatial solution to the time-independent Schrodinger equation. Here, you'll solve your equation for x, you'll solve your equation for y, you'll solve your equation for z, and once you find that, you can plug back in to find your overall spatial part psi as a function of x, y, and z. So that's all well and good. Cartesian coordinates works fairly straightforwardly. The separation is a relatively straightforward process. In spherical coordinates, that's not so true. We have a much more complicated expression for our Laplacian of the wave function psi. And, well, this is really the case that we often care most about, because this potential here is often going to be simply expressed in spherical coordinates. For instance, this could be a function only of radius. In the case of the hydrogen atom, which is what we're leading up to, this is decidedly a function only of radius. So let's see what sort of separation we can do in this case. First of all, let's think about pulling off a radial part. Psi of r, theta, and phi now, working in spherical coordinates, can hypothetically be written as some function of r multiplied by some function which I'll write as y of theta and phi. Let's see what this separation works. Or let's see if this separation works, if we can peel off the r-dependent parts. Now when I plug this in, my partial derivatives with respect to r are only going to act on the r part. They're going to leave the y part untouched. And likewise, my partial derivatives with respect to theta and phi are going to leave the r part untouched. So what we're going to end up with then is, as before, minus h bar squared over 2m out front. Pardon me. Y over r squared, partial derivative with respect to r of r squared, partial derivative with respect to r of capital R, is our first term. Then the second two terms here are going to leave r untouched, so I'll end up with r over r squared sine theta, partial derivative with respect to theta of sine theta, pardon my notation here, sine theta, partial derivative of theta with respect, or partial derivative with respect to theta of y, my theta and phi parts. The third term, r, again being untouched, r squared sine squared theta, and then the second partial derivative with respect to phi of y, my theta part. My theta and phi parts, excuse me. And that plus v times r y, my wave function, is going to be equal to e times r y, my wave function. So that's what I get when I substitute this separation guess in here. As before, this isn't exactly separated. I have a theta and phi dependent term tagging along with my partial derivatives with respect to r. And here I also have an r squared tagging along with my theta and phi dependence, both for my theta derivative term and for my phi derivative term. So I've got to somehow get rid of that. And I can do that by, as before, dividing through. In this case, I'll be dividing through by the quantity minus h bar squared ry over 2m with also an r squared. So the division, to simplify things, is a little bit more complicated, but the overall result you get follows the same general structure, only more complicated. When I do that division, I end up with 1 over capital R, r squared, partial derivative with respect to r of r squared, partial derivative with respect to r of capital R, my first term, getting rid of the y, minus 2m r squared over h bar squared from my constants, plus where those constants get multiplied in. V, which is a function of r, minus e. That's what I get for the parts that have r in them after I've done this supposedly simplifying division. I also have terms, of course, from my theta and phi, which end up looking like 1 over y, and what am I left with? I'm left with a 1 over sine theta, partial derivative with respect to theta of sine theta times the partial derivative of theta with respect to theta of y, plus 1 over sine squared theta, second partial derivative with respect to phi of y. That, overall, these two terms added together, has to be equal to 0. And this is the same sort of structure as we had before. This now is a function only of r, and this is a function only of theta. We'll take a look at what you get from the function only of r later on. But for now, the same sort of analysis holds. This function only of r being essentially equal to this function only of theta means both of those functions must be trivial if this overall is going to hold for every r in theta. So we'll be left with, when we're done, this being equal to some constant, and this being equal to some constant as well. And in this case, the constants that we choose are a little strange. At least they will look strange for now. I'm going to say the constant here is going to be equal to minus L plus 1, where L is some constant. And the constant here is going to be L plus 1, essentially the opposite. So I have some constant and some opposite of that constant being added together to give me 0, which should make a certain amount of sense. The form of these constants always bothered me when I first encountered this subject. How do you know what to use for the form of your constants? Really, it doesn't matter. If you use a form of the constants that's slightly less convenient, you'll end up getting slightly less convenient expressions for the values of those constants and how those constants are related to each other. But it doesn't actually matter all that much. You're just saving yourself some trouble by choosing a convenient form for the constants. After you build up some intuition going through this separation of variables procedure multiple times, you will end up with a decent amount of intuition for what those constants should look like. But for now, let's focus on the angular equation. The angular equation has this complicated form, and it's going to be equal to this constant, L plus 1, with the minus sign out front. The way to simplify this equation, first of all, I want to get rid of these sine squared thetas in the denominator. So I'm going to multiply through everything by sine squared theta. When I do that, sine squared theta, I want to get rid of this y in the denominator as well. So I'm going to multiply through by sine squared theta y. That's what I'm doing. When I do that, I get sine theta, partial derivative with respect to theta of sine theta, partial derivative with respect to theta of y, plus second partial derivative with respect to phi of y. Canceled out basically everything. 1 over sine squared theta and 1 over y are both canceled out by this multiplication. That then is going to be equal to minus L plus 1 times sine squared theta y on the right-hand side. Now what I want to do with this is the same sort of thing that I did with the radial part. I want to do separation of variables yet again on this partial differential equation in an attempt to separate out the theta and phi dependence, keeping in mind this y is a function of theta and phi. So I will write y, hypothetically, y of theta and phi is going to be equal to capital theta, a function of theta, and capital phi, a function of phi. And I'll substitute this in for y and see what this gets me. If you go through that, the same sort of analysis, the same exact sort of procedure, substituting this in, my partial derivatives with respect to theta will leave my phi's untouched. My partial derivatives with respect to phi will leave my thetas untouched. And as before, I will want to divide through by theta phi to more effectively separate things out. When you do that, what you will end up with is this part is just going to be by itself. Since it has a theta dependence, I'm going to lump it together with this term. And what we'll end up with is sine theta over our theta function partial derivative with respect to theta of sine theta, partial derivative with respect to theta of our theta function as our theta part. Having divided through by this, we've canceled out our phi dependence. That's where this 1 over the theta function came from. Our constants overall, well, they're not constants. Our term over here, which had a theta phi in it, which was then divided out, is going to instead appear on the left-hand side, being grouped together with our theta-dependent parts, plus L plus 1 times sine squared theta. Put brackets around that. Our phi part ends up looking relatively simple. 1 over capital phi, second phi derivative of our capital phi function. And this is all equal to 0. We've gotten rid of, that's all the terms we have to work with. So once again, we have a function only of theta here, and a function only of phi here. So as before, this has to be some constant, and this has to be some constant. And in this case, looking at this partial differential equation, you can probably guess that what we want to use for the constant here is something like m squared. In this case, I'm going to say this is equal to minus m squared, and this is equal to m squared. I've got a second partial derivative being divided by a constant. This part gives us an ordinary differential equation for capital phi as a function of phi. And just looking at that equation, very briefly, it looks like this. 1 over capital phi, second partial derivative of phi with respect to phi. Sorry about all the phi's in the same equation, but this is conventional notation for this process. Being equal to some constant, in this case, minus m squared. If I rearrange this slightly, second partial derivative with respect to phi of our capital phi function is equal to minus m squared times our capital phi function. Second partial derivative of something gives you a constant minus a constant squared times your original function back. You should have, at this point, a pretty good guess what the solution to this looks like. It's going to be something that looks like e to the I m phi power. When I take the second derivative of this, I will bring down 2 I times m's, which will give me my minus m squared, times my original function. Exponentials like this are much easier to work with in this complex context, since I ended up with a minus sign here. For instance, if you had chosen a plus m squared for your separation constant here instead of a minus m squared constant, you would end up with real exponentials here. But you would find out later on that the only way that this could work is for m to be complex. For instance, if you recall back when we were talking about the Schrodinger equation in one dimension, one spatial Cartesian coordinate, we had to have the wave function psi be continuous. The continuity of phi in this context now, since phi is an azimuthal coordinate which goes around in a circle, we have to have phi at one end of the circle be equal to phi at the other end of the circle. Essentially, evaluating this function at 2 pi must give us the same thing as if we evaluated this function at 0, or else our wave function, that would result from this separation of variables, would not be continuous. So, if I plug this in, I'm going to end up with e to the I m 2 pi being equal to e to the I 0. E to the I 0, well, that's just 1. So, e to the I 2 pi times m is going to be equal to 1. You know what the behavior of e to the I m phi is. It's a complex number rotating around as phi increases. And if I'm going to have it get back to where it started in a complete revolution, m here has to be an integer. So if m is going to be an integer, for instance either 0 or plus or minus 1 or plus or minus 2, etc., I will end up with the solution, with a valid solution for my phi part here. Now this is not the full story, of course. This was just one piece of what we got from that overall angular equation. The more complicated piece comes from the theta equation. The theta equation is complicated, but excuse me for a moment, this is now the partial derivative of our capital theta with respect to theta, since we've already done our separation of variables. This is our equation for theta. We can simplify this a little bit, as before, multiplying through by the capital theta. to get rid of this theta in the denominator, essentially. And what you end up with is sine theta, partial derivative with respect to theta, of sine theta, partial derivative with respect to theta of our theta function, plus L plus 1, sine squared theta, minus m squared, and I'll put this in square brackets and multiply it all by my theta function, is going to be equal to 0. This, well, this is complicated. At this point, we have to give recourse to the mathematicians, go ask them for their advice, and they'll tell you that this differential equation actually has a name, and the solutions actually have names as well. The solution here is that theta, as a function of angle theta, is given by any proportionality constant. As before, the Schrodinger equation is linear, so we can choose whatever proportionality constant we want, such that we can normalize our wave function, multiplied by something called an associated Legendre function. And it has a subscript L and a superscript M. This is not raised to a power, this is just a superscript. And in order to get this theta function, I have to evaluate my associated Legendre function at the cosine of the angle. These associated Legendre functions are a little bit like the Hermite polynomials we encountered when we were solving the quantum harmonic oscillator problem. The associated Legendre functions are given in terms of the Legendre polynomials. I'll write that out. P sub L superscript M of x, now just a generic argument, is more or less defined to be 1 minus x squared raised to the power given by the absolute value of m divided by 2 times the mth derivative of the P sub L of x, where P sub L of x now is a Legendre polynomial. So these P sub L superscript m's are the associated Legendre functions, and they're expressed in terms of the P sub L's, the Legendre polynomials. Mathematica knows about these, Sage knows about these, any computer algebra software worth its salt should know about Legendre polynomials. It may even know about associated Legendre functions. But P sub L of x, we have an expression for that as well. That's more or less defined to be 1 over 2 to the L times L factorial as an overall constant out front by convention to make normalization easier, times the lth derivative with respect to x of the quantity x squared minus 1 raised to the lth power. So if I want to know what the lth Legendre polynomial is, I can expand this out by raising it to the lth power, take the lth derivative of what I got, multiply it by some constant, take the mth derivative of that if what I want in the end is the associated Legendre function of order L and M, etc. Looking at the structure of these functions, you're taking an mth derivative, which means m has to be an integer. To put this in context overall, in spherical coordinates we need theta to vary between 0 and pi. What that means is that x, being given by the cosine of theta, has to be between minus 1 and 1. So we're only looking at these Legendre polynomials over a specific domain. And finally, these Legendre polynomials are actual polynomials. This is going to be a polynomial of order 2L, so when I take the lth derivative of it, I'm going to get a polynomial of order L. So the lth Legendre polynomial is a polynomial of order L. If I differentiate an lth order polynomial more than L times, I'm going to get 0. So this says, the structure of these functions, as I've written them here, says that if the absolute magnitude of m is greater than L, P sub L m is equal to 0, identically. What that means is that m can only be up to L. Only be within L and 0, for instance. If L is 0, m has to be 0. If L is 1, m can be plus or minus 1 or 0. If L is equal to 2, m can be 0, let me write that out properly. M can be 0, plus or minus 1, plus or minus 2, etc. If L is n, M can be minus n plus 1, etc., up to n. That's what the patterns are looking like here. So we only have a restricted value set that's available for L and that's available for M. In particular, L is an integer and M is an integer that is between minus L and L. The Legendre polynomials are something that you can go and look up. And in this case, I've given you a few of them to look at and plotted a few of them. They have the same sort of nice properties that the Hermite polynomials have. There are orthogonality conditions, there are normalization conditions. But just to give you a feel for what they look like, the 0th order Legendre polynomial is just a constant. First order is a line. Second order is a parabola, the yellow curve here. Third order, of course, is a cubic, the green curve. Fourth order is a quartic, the blue curve. And fifth order is a quintic, the fifth order polynomial given by the purple curve here. So the Legendre polynomials are the sort of polynomials that you'll encounter when you do separation of variables with the Laplacian in spherical coordinates. For instance, suppose what I wanted to do is find the theta part of my time-independent Schrodinger equation solution with L equal to 2 and M equal to 1. So here I'm talking L is 2 and M is 1. P subscript 2 superscript 1 of x is given by 1 minus x squared raised to the power m over 2, 1/2 in this case. Then I take the mth derivative, i.e. the first derivative, of P sub L of x, the Lth order Legendre polynomial. Now you could flip back to the most recent slide and look up what the definition for the Lth order Legendre polynomial was, but let's actually calculate it out. In this case, I'm going to be taking the xth derivative of it, whatever it is, and if you go and look up the definition of the Lth order, in this case the second order Legendre polynomial, you find it's 1 over 2 squared times 2 factorial of the second derivative of the polynomial x squared minus 1 quantity squared. And I should make it clear the derivative acts on it after it's been squared, not before. So we can figure this out. This is the sort of thing we can just plug into and do the algebra. 1 minus x squared to the 1/2 power. And overall, I'm going to get a 1 over 2 squared, which is 4, times 2 factorial, which is 8. So I'm going to have a 1 over 8 out front. And then I'm going to have a first derivative of a second derivative, so I'm going to end up with a third derivative, d cubed dx cubed, of what I get when I square this out. And when I square this out, it's squaring a binomial. I'm going to get x to the 4th minus 2x squared plus 1. So, third derivative of x to the 4th. X to the 4th is what I start with, 4x cubed after one derivative, 4 times 3, x squared after two derivatives, and 4 times 3 times 2, x after three derivatives. If I take three derivatives of x squared, I end up with 0, and if I take three derivatives of a constant, I of course end up with 0 as well. 4 times 3 times 2, that's 24. So 24x is what I get here. So I'm left with 1/8, 1 minus x squared to the 1/2 times 24x. 24 divided by 8 is 3. And if I go back and think of what I want here is subscript 2 superscript 1 of cosine theta, I can evaluate this at cosine theta. P21 of cosine theta is going to be, where'd my equal sign go? Is going to be equal to 3 times 1 minus cosine squared theta to the 1/2 times cosine theta, just x. Now this 1 minus cosine squared theta, 1 minus cosine squared is sine squared. That's one of the Pythagorean identities for sine and cosine. And if I take the square root of sine squared, I just get sine. So what I'm going to get in the end here is 3 sine theta cosine theta. End of story. So this is our theta part. Now if I wanted to know what the full y of theta and phi would be, in this case, my phi part is given by e to the I m phi, where m now is 1, so it's just going to be e to the I phi. And my theta part here would be 3 sine theta cosine theta. So I have a theta part and my phi part, and I'm going to have some normalization constant out front, which I have not yet specified. And that will give me a particular y with L equal to 2 and m equal to 1. There are, of course, an infinite number of allowed solutions here, and these y solutions with various L's and various m's are called spherical harmonics. They're expressed in terms of e to the I m phi and the associated Legendre functions evaluated at cosine of theta, but really they're just y, L, m. Usually it's written y subscript L superscript m. It's a function of theta and phi. And if you properly normalize them, going through the normalization procedure as we would if we were trying to normalize a wave function, you end up with this sort of expression. This epsilon here, incidentally, is keeping track of signs for us. It's defined to be minus 1 to the m if m is greater than or equal to 0, and 1 if m is less than 0. So it's just keeping track of signs. There's nothing magical about this epsilon. These spherical harmonics have an orthogonality relationship. If you use the same L and the same m, and you plug all these things together, and you go through the rigmarole knowing about all the properties of associated Legendre functions, you can prove that they do obey an orthogonality condition, subject to this normalization, of course. The one point that I do want to highlight at this is the sine theta here. The reason there's a sine theta here is that we're working in spherical coordinates, and essentially this is a volume integral. When we were normalizing our wave function in one dimension, we simply had a probability density as a function of a single variable. Our probability density now, as expressed as, for instance, the complex conjugate of the wave function multiplied by the wave function itself, where here we're only looking at the angular part, is a density function in 3 dimensions. And if you want to know what the total probability of finding the particle anywhere in this context, you have to integrate over volume. And if you're integrating over volume in Cartesian coordinates, that's easy. The volume element in Cartesian coordinates is just dx, dy, dz. But the volume element in spherical coordinates is not just dr, d theta, d phi. It's dr, d theta, d phi times sine theta. And that's where this sine theta is coming from. We're working in spherical coordinates, and that rears its ugly head here as well. Finally, the L and the M, just to recap, L can be any integer, 0, 1, 2, etc. Can't be negative. M can be negative, and it can only vary from minus L up to L. So these spherical harmonics have a lot of nice properties, and they appear over and over again. Let's take a look at what they actually look like. This is the sort of structures you get. The central column here is for m equals 0. The first row here is for L equals 0. The second row is for L equals 1. So we have m equals minus 1, m equals 0, and m equals 1. The third row here is for L equals 2. So I have m equals minus 2, minus 1, 0, 1, and 2 for my allowed values of m. The color now is showing you two things. The intensity of the color shows you the magnitude of the complex spherical harmonic. The color itself tells you about the phase of the complex spherical harmonic. So I'm showing you both amplitude and phase of a complex number plotted in 2 dimensions, and since I'm plotting it in 2 dimensions in spherical coordinates, I'm plotting it over a sphere. For L equals 0 and m equals 0, it's simple. We have no phi dependence and no theta dependence. Everything is just constant. We have a uniform red color everywhere in the sphere. For L equals 1, we start seeing some colors other than red. For m equals 0, L equals 1, we have intense red at the poles. at the North Pole and at the South Pole, with a black band around the equator, showing you that you have 0 magnitude of the complex spherical harmonic for L sub 1, m equals 0, at theta equals 90 degrees around the equator. If I have m equals -1 or m equals +1, I actually have dark spots at the poles instead of intense color at the poles. And the difference between m equals -1 and m equals 1 is the order in which the colors go. Here I'm going from green to blue as I move to the right on the front face. Here I'm going from green to blue as I move to the left on the front face. If L equals 2, the structures are slightly more complicated. Here I have 2 black bands at various thetas for m equals 0, 1 black band at the equator, and black spots at the poles for m equals -1 and m equals +1. And if m equals -2, geez, I keep writing this wrong, m equals -2, you have an even more intense dark region near the poles, but nothing happening at the equator. Note also that the colors vary much more rapidly here for m equals 2 than for m equals 1. This is a slow change from green to purple as I go from one side of the ball to the other, and here I have that same change from green to purple and then back to green as I go around. So here I've got only 90 degrees, what took 180 degrees here. So the phase dependence you get here and the angular dependence is rather difficult to visualize, but hopefully the patterns are starting to become clear. The number of dark regions, going down here you have 0 dark regions with theta, here you have 1 dark region with theta, here you have 2 distinct dark regions with theta. You could predict how many angles at which there would be no amplitude to the complex spherical harmonic as a function of theta. As you go away from the m equals 0 column, you stop getting these dark bands with theta. Here I had 2, here I only have 1, here I don't have any, but you start seeing a dark spot at the pole, and you start getting angular dependence here. The colors start swirling around, and the further away you go, the more the colors swirl. This is only one way of representing the spherical harmonics. Just to show you another way that might look a little more familiar, this is the same sort of plot, only now showing red and green as opposite phases. Essentially, this is a different superposition of the phi part of the spherical harmonics. What you had for our complex spherical harmonics, the way our textbook, Griffiths, defines them, was just e to the im phi. There were never going to be any angles phi where there were zeros for the amplitude of that spherical harmonic. But if I superpose e to the plus im phi and e to the minus im phi, I can end up with zeros, the same sort of way that we ended up with zeros adding up sines and cosines. So this is now, instead of plotting everything on a sphere, this is showing you the amplitude in a radial sense in 3 dimensions. So whereas, for instance, this is, as before, L equals 0, L equals 1, L equals 2, L equals 3, and going vertically, we have m equals 0, 1, 2, 3, minus 1, minus 2, and minus 3. So going down that column, I had a dark band going around the equator here where they're showing you 0 radius going around the equator. Here I had 2 dark bands going around at specific angles, and they're showing you 2 specific sort of cones where there is 0 radius for this surface. The color that's being plotted here indicates the relative sign of the spherical harmonic on either side. If these look familiar from your chemistry class, they should. These spherical harmonics will play an important role when we go on to calculate what the wave functions of the electron in the hydrogen atom actually end up looking like. So, try to wrap your head around what these things actually look like in 3 dimensions. Spherical harmonics are important. Understanding what their geometry is and what their structures is also important. To check your understanding, go back and use the definitions and find what the L equals 1, M equals 1 associated Legendre function evaluated of cosine theta actually is. And then think about how many points in the x direction does this 7th order associated Legendre, or the 7th order Legendre polynomial equal 0? And then how many points along the x-axis does the seventh order Legendre polynomial converted into the 7 associated Legendre function equals 0. And finally, if m is equal to 3, what are the allowed values of L? This is our typical Cartesian coordinate system, x, y, and z. If we're working in Cartesian coordinates, great. This is potentially something that we can work with straight away. We'll see what that looks like in a moment. For now, though, I also want to give you an expression for the Laplacian in spherical coordinates. If we're working in spherical coordinates, our coordinate system looks something like this. Just to draw a Cartesian coordinate system for reference, we're working with some point that is a distance r from the origin. And in physics we call the polar angle, which goes from the z-axis to the vector that goes from the origin to r, we call that theta. And the azimuth psi, acting on psi, is, as before, some kinetic energy operator, p squared over 2m, plus a potential energy operator, v times psi, gives us just a constant e, a separation constant from separation of variables, times psi. Back. Now, the really crucial part of this is this Laplacian, del squared. If I'm working in Cartesian coordinates, the Laplacian is relatively simple. Del squared I can write, and let me suppose that it's acting on a function here, to keep the notation simple, is going to be equal to the second derivative of psi with respect to x, plus the second derivative of psi with respect to y, plus the second derivative of psi with respect to z. The sum of the three second derivatives of psi with respect to the three Cartesian coordinate derivative of psi with respect to theta, and yet another term plus 1 over r squared sine squared theta times the second partial derivative of psi with respect to phi. The reason we have such a complicated expression here is that spherical coordinates are not exactly independent. If I move in phi, for instance, the direction of my r unit vector changes. Consequently, derivatives of functions with respect to a coordinate aren't necessarily directly related to geometrical objects like the Laplacian. The Laplacian is something that is really independent of coordinate system, and since the Cartesian x, y, and z coordinates are all really independent of each other, the Laplacian has a simple expression. In spherical coordinates that's not true, so the expression we get is the separation of variables with the time-dependent Schrodinger equation in 3 dimensions to remove the time dependence worked exactly the same way in 3-dimensional space as it did in 1-dimensional space. What we got then was a time part that looked exactly the same as it did before, e to the minus I h bar, or I e t over h bar, as before, and a spatial time-independent Schrodinger equation. So let's take a look at the time-independent Schrodinger equation in 3 dimensions. Consideration of this will lead us to the topic of spherical harmonics, which is very important in many different branches of physics. So we'll spend some time visualizing what they look like. First of all, though, the time-independent Schrodinger equation we got looked something like this. The Hamiltonian operator times the angle around the z-axis here. Let me draw that down here. We call that angle phi. So r, theta, and phi for distance, polar angle, and azimuthal angle is our coordinate system here. And in that coordinate system, our Laplacian in spherical coordinates is a good deal more complicated than our Laplacian in Cartesian coordinates. Del squared, acting on some function psi, is 1 over r squared times the partial derivative with respect to r of r squared times the partial derivative of psi with respect to r, plus 1 over r squared sine theta, partial derivative with respect to theta, of sine theta, partial